Let's now look at confidence intervals for the population variance. So the setup is the same. We have an unknown population. We assume the population is normal with unknown mean and unknown unknown standard deviation sigma x. We know the sampling distribution of the variance is a chi-square distribution. And we want to use this knowledge to invert it, to say like, okay, we know if we knew the population variance, we know what type of sample variances we would obtain, and we want to invert it and say, given a particular sample variance, what is the population variance? Okay, that's how we build a confidence interval. I won't go into the details, but the idea is the same. You find the cutoffs in the chi-square distribution, the lowest alpha over 2 quantile and the upper alpha over 2 quantile. You do some inversion steps, and in the end we obtain an interval that contains the true population variance 1 minus alpha % of the time. We use that interval, so this is the formula that works in general for the procedure, and this is the actual confidence interval, lowercase, which we compute from a particular sample. Okay? Very similar to what we did before, but the distribution is the chi-square instead of the t-distribution. So that's why I'm not going into the details, very similar. Okay, let's look at an example. Again, the apple weights, the sample variance. So we want to know now what is the variance of the population. And the point estimate, so a single number estimate is 346. But is that, could it be 300? Could it be 200? Like, how precise is this estimate? So we're just going to apply this formula here. What do we need for the formula? We need the sample size. We need the sample standard variance. We got it here. And we need the 2 quantiles of the chi-square distribution, so with n minus 1 degrees of freedom. Okay, so this is how we build the computer model for the chi-square distribution. This is how we obtain the 5th quantile, 0.05, or the 5th percentile, and the 95th percentile, and then we just plug in the numbers in the formula, which we obtained. Note the upper 95th percent quantile is actually goes into the computation of the lower limit. This is a little weird. They flip sides because the way we obtained the interval, we had to do an inversion of an inequality, so then the limits change sides. Oh yeah? Let's see it. Okay, so there you go. So the estimate is the variance computed from this sample is 345, but really a more accurate description is the variance, because it's a small sample, size 30, the variance could be anywhere between 230 and 600. So this tells us the precision of the estimate of the variance. Okay? And as we saw before, let's do this again. Let's do a rerun, but this time using the bootstrap approach. So very similar to what we saw above, generating the bootstrap distribution from the sample. We want the bootstrap distribution of the variance. Okay, so we store it in this list and then cut off the bottom 5% and the top 5% to get another interval. A little bit different. So in the previous video, the bootstrap approach and analytical were very much the same. Here it's a little bit off, but still gives you, you know, it's not. It gives you an idea. You know, you can expect this variability. Okay. So maybe not the best bootstrap for variance, not the best. But hey, it was fast. And here is a procedure that anytime you need to compute the confidence interval for the variance of some distribution, here is what you can do. All right. And verify the coverage probability. I'm not gonna run that. Fool me once. I'll tell you the test we did. I did was 90% accurate, so it's very good. The analytical approximation is very good, and the bootstrap approximation was 82%, so not that good, but still roughly close, right? Okay, so next video we're gonna do confidence intervals for the difference between means.